Our speaker today is Annette Foerster. She's currently at the University of Hawaii in the Department of Atmospheric Sciences. She received her diploma and diploma degrees from the Karlsruhe Institute of Technology, and while working on her diploma thesis at the Naval Postgraduate School in Monterey, she met up with Michael Bell and working on the analyzing ELDORA data from there. Apparently that worked out well because after her diploma thesis, she joined Michael Bell at the University of Hawaii doing her doctorate research. And she's currently visiting here for about a month, 2 more weeks left, I think you said, as a guest of Wenchao Li, who also happens to be on her thesis committee. So from there, Annette.
Thank you. And yes, thank you very much for the invitation, Wenchao. And I'm very glad to be here and be able to give that seminar. And the topic is airborne radar observations of tropical cyclones. And I think, oh, that was not the plan. Okay. I guess you're not the audience that I have to convince that observations are actually important. So I'm just going to go ahead and say why I'm interested in eyewall convection. And I mean, we have that really basic model of a tropical cyclone, which is basically just in, up, and out. And in an axisymmetric sense, that seems very easy, but of course there's complications. And there's those convective cells embedded within the eyewall, and the question is how important are they? And what do they do to the larger scale? So how do they influence the structure and intensity change? And also, what does the environment do to that convection? So how does, for example, shear influence the convection within the eyewall? That's what I'm interested in. And just to give you a couple of background information on why eyewall convection is cool, there is one study by Pendergrass and Willoughby in 2009, and they showed, just using the Sawyer-Eliason model, that timing and location of repeated convective bursts seems critical in intensification efficiency. And they actually showed that convective heating inside the RMW is most efficient. And I have one of their figures from their paper up here, and what you can see here, here's the radius. And well, I just want you to focus on these lines here. This is the maximum wind tendency. And what they did is they just put in heat sources at different radii and looked what that does to the wind tendency. And you can see, I mean, if you put a heat source in somewhere out at 140 kilometers, it does give you a positive feedback, but the closer you get towards the radius of maximum wind, the bigger the effect. And if you actually get inside the RMW, you see that the effect increases a lot. So it matters where the convection takes place. So it might be interesting to look at what forces convection and how do you actually get convection inside the RMW. And there's also a lot of a couple of studies that investigated how vertical shear influences convection. And I mean, usually we think of vertical shear as something that weakens the storm. And interestingly, there's a lot of studies that also showed that it not just weakens the storm like everywhere, but it actually organizes convection. So a couple of studies in mature hurricanes found that the convection is enhanced down shear and suppressed up shear. So you can see here is from Corbusiero and Molinari. And they actually, they investigated the flash rate with respect to the shear vector. And they found that down shear, or in the down shear semicircle, you've got a lot of flashes, and in the up shear quadrant, almost nothing. And kind of the same result is what Black et al. Found using airborne radar data from, I think that is Hurricane Olivia. They have westerly shear. So this is the shear vector, and they found that most of the reflectivity, or the highest reflectivity values, are left of shear. So you would actually expect that you get cells that grow here and then mature as they wander around. So basically, down shear or left of shear is where you would find the strongest convection. That's what they found in mature hurricanes. And well, one other thing that really largely influences the structure of a tropical cyclone and also the eyewall is if it undergoes ET. And this is a figure by Klein et al. And they kind of split up the extratropical transition in 3 distinct stages. So basically, extratropical transition just means that it moves north and encounters a different environment. And they actually made a nice point in splitting that up into 3 distinct steps. And so here the top panels are Typhoon Ginger, and the bottom panels are Typhoon Stella, and you can see those 3 steps nicely. So at first it gets an asymmetric structure just because there's cooler sea surface temperatures and cooler and drier air here to this side and more moist air to this side. So you get that asymmetric structure. Then also increased wind shear impacts the storm. So you get much more convection here to the northeast and less here on the southwestern side. And then if it actually interacts with the baroclinic zone, you get frontogenesis, where the warm front is much more pronounced than the cold front. So, but as you can see, they only looked at satellite data. And the question is, how does that actually look, or how does the eyewall look like during such a transition? And there hasn't been too many observations, especially not airborne radar observations of that. That's what I want to show you later on. So this is the outline of my talk. First, want to just briefly go over, well, how do you collect data and how do you process the data? And then I'm going to split my talk in 2 parts. The first part is a storm undergoing extratropical transition. And I will use data from typhoons in Laku, from the TPARC TCS08 field campaign. And then the second part, I'm going to focus more on like the internal mechanisms, and I'm going to show you how to retrieve buoyancy from radar data. And that is using data from Hurricane Rita. So let's get started with how do you observe eyewall convection. I mean, of course, we get satellite imagery, but I mean, that is not, well, our goal is to get high resolution 3D observations. I mean, this gives a really nice coverage and shows us a lot of detail, but it's not like that detailed. And then if we go to, for example, microwave imagery, I mean, we see a lot more structure and we can make out the eyewall, but still that is not like really high resolution, and that is where airborne radar comes into play, and where it's really awesome because you can see all those detailed structures, so you can really get into the nitty-gritty details of how the eyewall convection looks like. So that's what I want to use for the rest of my talk, is airborne radar data, because it has a really high resolution and it has a nice large coverage. And additionally, we also use drop zones, flight level data, and atmospheric motion vectors just to supplement the radar data. And I guess I don't have to tell you guys what ELDORA is, but that's the data that I'm going to be using. And since it has a really nice large coverage, we can actually like sample the entire eyewall if you do eyewall penetrations. And as it flies past any interesting features, we get that crosshatch pattern where we then can retrieve the winds with a dual Doppler analysis. So that's the main data source. And how do we get that on a nice regular grid? I know that there's software out there like Cedric or Gamache, but what I want to use for like the rest of my talk is a software package developed by Michael Bell called Samurai, like with a fancy acronym for spline analysis at mesoscale utilizing radar and aircraft instrumentation. And it gives us a maximum likelihood estimate by minimizing a cost function. The basis are cubic B-splines, which makes, for example, the wind field really nice because the second derivative is still continuous. So that that way we can, for example, calculate divergence budgets nicely. And one other really good or really great advantage is that it can incorporate multiple data sources. So in that analysis, we can also use flight level data of the, for example, for the winds, so we can actually add more data sources. And then, I mean, you can output it on either a regular Cartesian grid or cylindrical, which is sometimes nice for hurricane studies that you're already in that cylindrical space. And with that, I'm gonna jump right into part number 1, which is Typhoon Sinlaku. And it was one of the typhoons that were observed during T-part TCS 08. And this is here the track of Typhoon Sinlaku, and you can see, oh, and that is the matching winds for that period. You can see it intensified, and then it hit Taiwan and weakened, and then it was supposed to do to undergo extratropical transition, but instead of just like gradually weakening, it actually re-intensified here on the 18th. And this here is the date that I want to look at, where it's again reclassified as a typhoon, so it has maximum, or it has pretty high wind speeds, but it's already located very far north and about to weaken. And here you can see the flight tracks. From this day on the 19th, we had 2 aircraft in the system, and this gray shade is the radar coverage, so you can kind of make out where the eye is, but I'm going to show you some more detailed plots. This is just to show where the radar data is. And you have here in the solid line is the P3 flight track, so they actually entered the eye from the southeast, then made a loop in the eye, and then flew out to the west. And here we have the C-130 flight track. But I mean, as you can see, they didn't penetrate the Eyewall. And due to those 2 aircraft, I've got a really nice data set that I can analyze, and big thanks to this crew. Here we've got some pictures from the aircraft, what the radar display looked like. So this already gives you a hint of what you're going to see next. And well, I guess it doesn't look too terrible to fly through a hurricane. They all smile. And so let's get into the details of the structure of Typhoon Sinlaku. So this is the big picture, the satellite imagery. And you can see, as I've just shown in the typical ET extratropical transition cases, you still see the Eyewall, but you have most of the strong convection off to the northeast of the center. It's really asymmetric, and you can already see that the Eyewall is not closed anymore in this quadrant. If you take a closer look and look at the reflectivity pattern at 1 kilometer altitude, you can see that the structure is very asymmetric. You get pretty high values here to the northeast, and some more centers of higher reflectivity. Then you've got this little area that almost looks like it's disconnected from the rest of the Eyewall. You get this patch here, which is basically a gap in the Eyewall. And if you take a look at the 3-dimensional reflectivity pattern, just to see what the vertical structure looks like, you can actually see that here to the northeast, again, you get pretty high reflectivity values. So, well, I should say the yellowish ice surface is the 28 dBz surface, and the red or orange one is 38 dBz. So you can kind of see, you've got, well, it's hard to see, but this is actually a continuous 38 dBz surface here. So you've got high values in this quadrant. And then you've got those 2 peaks here in the western Eyewall, which actually probably are dissipating cells. So you get the mature cells here on this side, and then the dissipating cells on here. And this is just a remnant. And so you can see that the structure is really asymmetric around the center. And if you look at a more statistical way, we can compute the mean dBz and the standard deviation of reflectivity for each quadrant. Oh, sorry, I should go back and explain this error here, because this is actually the shear vector, and because we suspected that the convection might have some, or the organization of the convection might actually have something to do with the shear, we split up our data in shear relative quadrants. So this is the shear vector, and these are then the 4 quadrants that we will see later on, or that you will see. So this is up shear left, no, sorry, this is down shear left, up shear right, and down shear right. But I'm also going to show a schematic because even I get confused. So this is what the reflectivity profiles for every quadrant look like. And so here you have the 4 quadrants again. And what you can see is that you have the highest reflectivities left of shear, so that's the blue and the red curves. So this is, I mean, that corresponds to what we saw early on in the study by Black et al., where you always have the highest reflectivity values left of shear. And if we go to the variance, we actually see that the largest variance is down shear left, and usually the variance of the reflectivity is connected to, or you can distinguish stratiform and convective, because you know that stratiform, basically everything looks the same, so the horizontally it looks similar, I should say. So the standard deviation is pretty small, and for convective, the standard deviation or variance is pretty large. So you can actually see nicely here that you get the highest variance down shear left, which points towards active convection, and the smaller variances up shear left and up shear right suggest that it's more stratiform. And we also looked at vertical mass flux to see if you could see that convective versus stratiform signal in the vertical mass flux too. And again, these are the 4 quadrants, so this kind of corresponds to the northeast. That's why we put down shear left here. That's the kind of northwest, and so on. And what you can see here in the northeast again, in the down shear left quadrant, here you've got a lot of, this is vertical mass flux weighted CFADs. So basically what you can see here is, here's the 0 line, and everything here to the right of that 0 meter per second line is upward mass flux, and this is downward mass flux. So in the down shear left quadrant, you can see there's a lot of upward mass flux and almost no downward mass flux. Whereas if you look at the up shear right quadrant, you actually have the strongest downward mass flux here in this quadrant. So that also nicely corresponds with here very active convection. Here's something mixed between stratiform and convective, and here you actually have a lot of downdrafts. So the convection is dying. And one other way to look at it, just to see where is the convective, where is the stratiform, is if we actually look at the divergence profiles. And this, I think, really nicely shows that you have here in the red was the down shear left, so the northeastern quadrant. You've got a lot of convergence down low and divergence up here. So that corresponds really nicely to what House sketched for convective. And for example, if you here look at the black and the blue, which are the up shear quadrants, you can see we actually have divergence down low and the convergence at mid levels, and then convergence again. So that really nicely shows how different the convection is around the center. And this actually kind of surprised us, but it looks surprisingly similar to what a rain band looks like, where you have active convection here, and then so you go downstream, you have more stratiform elements. And just to show, or to sum up all of these things, I'm going to show you some vertical cross sections. You can nicely see the difference between the quadrants. And I'm going to start here in the down shear right, where you can see you get that elevated maximum of reflectivity. So the center is always here, where the 0 line is, and then this is the cross-section going outward. So you can see a nice reflectivity maximum here, and then a lot of upward motion connected with that. So we claim that that is convective initiation. And if you look at the down shear left, that is where we always had the most active convection. So you've got really strong convection here and a nice in, up, and out pattern, as you can see in the wind vectors. And if we go to up shear left, you can actually see that we don't have the inflow at the lowest level, but we have mid-level inflow. And also a lot of downward motion on the inner edge of the reflectivity maximum. So this is kind of the transition from more convective to more stratiform. And here in the up shear right, you can see the weakest reflectivity signal, which is that tiny little patch of decaying convection. So just to sum up, that Sinlaku tile, the storm interacts with shear. So all of those patterns that I showed you nicely actually corresponded to the findings that others had. So the convection was organized by the shear. And this actually surprised us at first because we thought we would find a more extratropical signature in that storm. But that actually supports the three-step model of Klein, where they actually show that first you get a more asymmetric structure, then you've got the interaction with the shear that the baroclinic zone produces, and then you get the interaction with the baroclinic zone itself, where you've got frontogenesis happening. And well, all those splitting up into quadrants showed nicely that the convection is initiated down shear, and then it matures as the cells travel downstream. And then on the up shear side, you've got dissipation. And the up shear semicircle actually exhibited stratiform characteristics, which has not been shown before in more mature hurricanes, probably just because Sinlaku was pretty weak at that time. You could actually see that transition from more convective to stratiform. So that was part one. And in part two, I don't want to talk about external forcing mechanism for convection anymore, but I want to go to more internal forcing, because I showed you before that it's really important where the convection is relative to the radius of maximum wind on if you get intensification or not. So location is important. And how do you get the convection there? There's a lot of possible convective forcing mechanisms. For example, boundary layer dynamics, such as supergradient winds, or vorticity anomalies, or one of the possible candidates is buoyancy. And I want to show how to retrieve that from radar data. So first of all, buoyancy in a tropical cyclone is not as easy as in just your everyday convection, because usually you have the Archimedes principle. You say, well, if a body is lighter than its environment, it's going to get accelerated upward. This actually assumes that you have horizontal pressure surfaces. But of course, in a hurricane, we've got sloped isobars, because the air parcel is not only subjected to gravitational forces, but also to centrifugal and Coriolis force. So you've got sloped isosurfaces, and Smith et al. 2005 actually pointed out that it's really critical on how you choose your reference state to calculate buoyancy to get something meaningful out of it. And this is an example, or this should just illustrate why it's important. Here in shading, you have buoyancy for two different reference states, one just hydrostatic and one hydrostatic and gradient wind balance. And the contours here are the updraft, so everywhere where there is, I don't actually know what this threshold is, but this is all upward motion basically. And you can see here, if you just use the hydrostatic reference state, you basically just get a big blob of positive buoyancy, but that doesn't really tell you where the convection is. And if you use a reference state that is in hydrostatic and gradient wind balance, you actually get that couplet you see positive buoyancy is associated with the region where you have the upward motion, and where you get negative buoyancy, there is no upward motion. So choice of reference state is critical. And now the question is, how do I get buoyancy from observations? And well, since buoyancy is basically just depending on the density, and density depends on temperature, pressure, and moisture, you ideally would like all those measurements, like very high resolution over a large area, but that's not where we're going to get. So there's one study by Easton et al. Who used flight level data to calculate buoyancy. And of course, to use flight level data is really nice because you have direct observations. The problem is just that the definition of the reference state is difficult because, as I just said, you need to know, or you need a reference state that is in gradient balance. And to know that state, you of course need the entire wind field, and not just like along the flight level. So the definition is difficult, and of course you can also only observe the convective cells along your flight track and not over the entire eyewall. And that's where I think radar might have a lot of advantages because it has great spatial coverage. Of course, the problem is, well, for retrieving buoyancy, you need temperature and pressure, but radar doesn't give us that. So our method to get around that is to utilize radar data and then use a thermodynamic retrieval to estimate temperature and pressure and then calculate the buoyancy from there. And basically, the thermodynamic retrieval that we're using, it's not too different from what other people have done, like Frank Roux or Lau. The only modifications that we make is that we use a cylindrical coordinate system because that's just more natural for hurricanes. And then, as I just said, the reference state is the hydrostatic and gradient balance. And then we basically get the three momentum equations and the thermodynamic equation. And there's some terms in here that I want to point out. So in this is the buoyancy term. We actually have a radial component of the buoyancy because you have that centrifugal and Coriolis force. And then in the vertical momentum equation, this is the buoyancy term, and you also have a perturbation pressure term. But I'm going to come back to that later. So basically, we have this set of equations, and then we're going to just use a variational approach to solve this set of equations. And how we actually get from the raw radar data to the buoyancy retrieval is a three-step process. And I want to walk you through all of that first, just to explain the conceptual model. Then I'm going to show you examples from Hurricane Rita for all of those steps. So first thing is we have the radar data, and we can, well, as I just said, use, for example, Samurai to assimilate that to get a 3D wind field and a 3D reflectivity field. We then calculate the mean state, so we basically just average azimuthally and then get a nice mean state for pressure and temperature. And if we have that mean state, we can then subtract off, or we can then retrieve the buoyancy using the thermodynamic retrieval. And as I just said, I used Hurricane Rita data to actually just test the retrieval to see if it's working. And what we did, and here you can see the track of Rita. And at, for example, the 21st, it was a Category 5 hurricane, so really nice and symmetric. And to test our algorithm, we thought it's too difficult to use observational data first, from the start. So we actually did a WRF simulation. And you can see here the best track and maximum wind speed and the simulated maximum wind speed. So they nicely match, and same with the pressure. So at least to first order, the simulation follows nature pretty well. And what we did is then actually use the WRF simulation and fly an aircraft through that simulation. So we get radar data that we can then use to test our algorithm. And so the first step is, as I just said, just to get the wind field, we have to simulate the radar data with Samurai. And here's some examples from Hurricane Rita from the 19th and 21st. You can see on the 19th, it's not nice and symmetric, but on the 21st, where it's a category 5, you can really nicely see the strong center and the cyclonic circulation. And well, as I mentioned before, you can also output that in a cylindrical space to make it easier for certain kinds of analysis. Then step 2 is to calculate the mean state, because we know that usually, or to first approximation, a hurricane is in hydrostatic and gradient wind balance. And what we do is we start with the sounding, and then since we know the mean wind field, we can actually integrate the thermal wind balance inward, and then get the pressure deficit and the temperature anomaly. What you can see here, that is for the Rita example. When you go inward, you see you have a pressure minimum, and if you look at the temperature, you get a maximum as you go inward. So yeah, we do have a hurricane with a pressure minimum and a warm core, so that's good. And just to mention, this reference state actually changes with radius and height, so whenever we calculate the buoyancy, we have to use a different reference state for every level. And if you then use the thermodynamic retrieval with those perfect observations from the WRF simulation, this is what we get. So here in shading, you can see the precipitation mixing ratio, and you have the buoyancy anomalies. Positive buoyancy anomalies are hatched, and negative buoyancy anomalies are stippled. And this is just a sequence over 4 hours. And if you just focus on this rain band here, you can actually see that rain band circles around the center here. And at first, it's associated with a positive buoyancy anomaly. And as the convection matures, it actually has a negative buoyancy anomaly, which we think just shows that there is water loading going on. And well, we can look at some other variables too, how buoyancy corresponds to the vertical motion. And you can see that here nicely again, where we saw the rain band and where we have the positive buoyancy, we also have upward motion. And then as the water loading gets bigger, we also have negative motion associated with that. And one more variable is the perturbation pressure gradient. And well, I didn't go into detail before, but the way you actually define buoyancy is by using the vertical momentum equation and then defining your mean state. And so the buoyancy is basically just the temperature perturbation, but with that you also get that vertical perturbation pressure gradient that you have to consider if you want to say anything about the vertical acceleration. And it turns out that it's actually two large opposing terms. So whenever you have positive buoyancy that is trying to accelerate your parcel upward, you also get a negative component by this perturbation pressure gradient. So if we want to interpret the buoyancy, we always have to be very careful and consider that term too. So in summary, radar, I think, is a great tool to analyze eyewall convection. And in Sinlaco's case, we saw that the environmental factors, or namely vertical shear, influence convection and actually shape it and determine the azimuthal distribution and also the character of the convection. If you want to know more, you can read all about that in this paper that just came out this month. And well, the internal forcing mechanisms are very interesting to see how much they contribute to intensity change. And there are several possible mechanisms. And well, buoyancy can be retrieved from radar data. It's a little complicated, but the preliminary results are promising, and we hope to do that for like real radar data too. So just to conclude with the outlook, as I just said, well, we want to calculate buoyancy from real data and also for different stages of the sea life cycle. Also to see if rapid intensifiers and steady state storms are different, or if the buoyancy in those cases is different. And then, well, in the end, trying to investigate the interaction between buoyancy, vorticity, isometries, and A-gradient winds. Thank you.
Okay, thank you, Annette. Do we have any questions? I'm sure we have some.
In the TC transition case scenario, you mentioned it's a two-stage process. One first interact with the shear, then the baroclinic zone.
Yeah.
Is the increase of shear part of the reason, not the reason, produced by when the storm is actually approaching the baroclinic shear, so the vertical shear increase?
I think so, and I think that's also the idea that Klein et al. Whatever. Because, yeah, I mean, that huge temperature gradient, of course, creates a lot of vertical shear, too. So it's, I guess, it should always be the case that at first there's the tropical cyclone is impacted by the vertical shear, and then by the baroclinic zone itself.
Thank you. I was just curious in your equations for buoyancy. I didn't notice any of the buoyancy terms due to the weight of the hydrometeors. Do you have
That is, yes, you're right. That is kind of hidden in that variable theta rho prime, because that is actually the potential temperature including water loading. So that is like in that little row that is hidden in there. But it is there.
Okay, so so you do have. Can you get from the radar the hydrometeor buoyancy component as well?
Well, I guess I mean, using the reflectivity data, I mean, you should know, or you should be able to estimate how much.
Yeah.
Water. Yeah.
What happens when you try to do this analysis in the boundary layer where the gradient wind balance doesn't hold? And I would think if you integrated thermal wind, you would get a cold core that's not real. And how does that affect your analysis? Or can you even do the analysis there?
Quick answer. Well, we have stayed away from the boundary layer for now. So we right now we look at 4 kilometers altitude. Just to be safe and not be close to the boundary layer, because of course, I mean, gradient wind balance doesn't hold there anymore. Like for the future, we thought about maybe like estimating the friction that you have and include that in the equations, but I mean, I don't know if that's going to work, because then you've got so many sources of uncertainty that maybe you want to stay away from the boundary layer for that retrieval.
Any more questions? Okay, that looks like it. Thank you again, Annette.
Thank you.